Good.
Good. Welcome everybody to one more seminar in our interdisciplinary area of computational engineering and science. It's our pleasure to receive today Professor Assad Oberai from the University of Southern California in Los Angeles, USA. He will entertain us about the adversarial learning of prior and posterior distribution in Bayesian inference. Professor Oberai is a professor, of course, in the aerospace and mechanical engineering department at the Viterbi School at USC. He was a professor in the aerospace and nuclear engineering at Rensselaer Polytechnic Institute in upstate New York, and where he was the associate dean for research and graduate students in the School of Engineering and the associate director of the Scientific Computational Research Center, SCOREC. Assad has a excellent track in research. I know him I believe I know him from his PhD days and with Town Hughes. And since then we have been many times together, and I follow his fantastic career over the years. And it's really an enormous pleasure to have you here with us today. Thank you for accepting our invitation. And Assad, please, the show is all yours.
Okay, thank you, Alvaro. Thank you for that kind introduction and this invitation to give this talk. I hope everyone can hear me okay. If there are any problems, let me know. And I feel like since this is a group of like-minded people, and not a big gathering of people from very diverse backgrounds, I feel like we should keep it informal and as you have questions, as you have comments, you can ask me in real time. I think let's not wait till the end of the seminar for questions. I think if I guess a couple of ways you can just unmute yourself and ask the question. That will be the best way of doing it. Or if Alvaro doesn't mind, if he can keep an eye on the chat, if there is a question there, then Alvaro, you can tell me to stop and I'll look at the chat too.
Sure, so I will. But everybody, feel free to interrupt Assad and ask him.
Okay, awesome. All right. Okay, let's just do it that way then. I think it'll be most useful and productive for everyone that way. Okay, so let's get started. As Alvaro said, I'm at the University of Southern California in LA, and we were just talking about the differences and the commonalities between Rio and LA. So as you all know, LA is also by the coast, by the Atlantic coast, by the Pacific coast. It is also like Rio, like a big city with really beautiful landscapes, a lot of things going on, mostly good things, but sometimes not so good things. And really a multicultural place where, where I think no matter where you're from in the world, you would feel comfortable. And within that, USC, is the University of Southern California, is like in downtown LA, a little to the south and a little to the west of downtown LA. And it is a really big private institution. It's about 30,000 students. And within that, Viterbi School of Engineering is one of the sort of the preeminent schools within the university. The Viterbi School, and I was like the vice dean for research for the school till about a week ago. And, it's a school which is well reputed in the US. We are ranked, I believe, number 12 in the US News World Ranking for graduate schools in the US. And, our strength is in many different areas, but certainly computational science, machine learning, AI, uncertainty quantification is one of those areas, right? And that's basically what my group does. Okay, so that's where I'm coming from. These are all the people that I've worked with in the talk that I'll be giving today. Dhruv Patel is a PhD student who is now a Timoshenko Fellow at Stanford. Deep Ray is a postdoc working with me, and Hari and Saeed are two PhD students who are working with me right now. Okay, so let's get started. So like a lot of people over the last, 10, 12 years, we've been thinking about the interplay between computational physics and machine learning. And of course, both of these fields have things to offer to each other. What I'll talk about today, instead of being very broad, I'll try and be very specific. I will talk about how machine learning can help in the solution of inverse problems. So that's what I'm going to be focusing on today, right? There is, of course, you can sort of pose it another way, and which is like computational physics. How does that help machine learning? And I think we've been doing work in how it can be used to quantify uncertainty in machine learning, but that is not the topic of today. So the topic of today is basically how do you use certain machine learning tools and algorithms to solve inverse problems that you might get out of computational physics. And the three ingredients of today's talk are going to be inverse problems themselves. There's going to be Bayesian inference, and then generative adversarial networks, which are a machine learning tool. So those are the three ingredients. And here is an outline. So I will begin with giving a brief introduction to each of those three ingredients and sort of trying to find relations between them. So that three ingredients being inverse problems, Bayesian inference, and then GANs. And then within Bayesian inference, you will see that there are two important distributions that show up, probability distributions. That's the prior distribution and the posterior distribution. And I will contend that GANs can play a role in approximating both those distributions. And then I'll show you some examples to substantiate my claim. And that's pretty much it. So, okay, so that's the outline. So let's get started with the three ingredients, right? So the inverse problem. Now, I'm old enough to be lucky enough to have attended a lecture by Joe Keller on the topic of inverse problems. And then there is a beautiful manuscript, an article that he's written on inverse problems, and I would recommend anyone to read that up. That's this first reference that's cited here. And his definition of inverse problems is like, if there are two problems and if the solution of one involves the solution of the other, then the two are a pair of a direct and an inverse problem. Now, the question is, which is the direct problem, which is the inverse problem? And this is where I think Joe Keller is purposely vague. He says, the one that is very well understood, that you've been solving for a long, long time, is the direct problem. And the one that is new, that is not as well understood, is the inverse problem. And for me, that's a great definition, all right? And then he gives, some serious and some not so serious examples of inverse problems. So one example that he gives in his paper is, what is the question to which the answer sounds like 9W, right? And in the paper, the answer he gives is, do you spell your name with a V, Herr Wagner, right? So in German, that would be 9W, right? But if you attended his talk, he then goes on to give you more answers. He says, well, that's one answer. The other is, of course, what size of shoes do you wear? 9W, 9 wide, right? Or what is the highway that's the west of Hudson, that I know really well because living in upstate New York, that connects New York City to Albany, and that's Route 9W. And through this sort of toy example, he illustrates one important problem with inverse problems, which is it can have multiple solutions. So these are typically ill-posed problems, right? So moving on, what is the canonical direct problem and what is the canonical inverse problem that we are working with? So the canonical direct problem that you can think about is, let's say, the forward heat conduction problem, right? So I give you the boundary conditions, the initial conditions, the equation for heat conduction, and I give you the thermal conductivity and say, what's the temperature at a later time, right? The inverse problem goes the other way, right? So I could give you the temperature distribution, or maybe a sequence of temperature distributions, and then say, what was the thermal conductivity that generated this, right? So that's a typical inverse problem that we'll be working with. And you can find similar problems in all areas of mechanics and physics. Okay, so like I alluded to earlier, there are some problems with inverse problems, right? Typically, the inverse map is not well posed. It may not have existence, uniqueness, or stability. And secondly, when you measure something, you measure always a noisy version of that. So your measurement is noisy, and using that measurement, you're trying to infer something. So that causes problems. And then thirdly, you might have, whatever you're trying to infer, you might have some prior knowledge about it, right? Which has nothing to do with the measurement. This is knowledge acquired prior to the measurement. And you want to encode that in a certain way, right? While solving the inverse problems. So all this makes it challenging to do. And roughly speaking, there are two approaches to address these challenges. You can either regularize the problem, or you can rely on Bayesian inference. And that is what we'll be working on. We'll be relying on Bayesian inference to basically look at an inverse problem as a statistical problem and then solve it in that sense. So before I move on to Bayesian inference, I want to set a little bit of notation. So I want to say that the vector So everything is going to be discrete. I'm not going to be talking about continuous functions here. So the vector that we wish to infer is going to be denoted by x. It will live in a compact subset of Rnx, where nx is going to be the dimension in which we are working, right? And nx will be typically large, so 1,000, 10,000, maybe a million. The measured response will also be a vector. It will be in a subset of Rny, and ny will be similarly large, like 1,000, 10,000, or a million, or something like that. The direct map, which will map omega x to omega y, will be denoted by f. And sometimes we will assume that the measurement is going to be the direct map operating on x plus noise. So it's going to be an additive noise model, and the distribution will be denoted by p eta. So that's sort of preliminary notation, and that's all we need.
Hi.
Yes.
Hi, Assad. Yeah, my name is Daniel. So as you asked that we could interrupt, I'm taking advantage of that. Is that okay?
Yeah, absolutely. Please, Daniel,
yeah.
Go ahead.
So yeah, we are in a class on statistics, and we are currently covering linear regression. So this equation looks a lot like the standard model for linear regression, right? Where we have the outcome, we have the input, and we have a noise. But yeah, I have some questions related to first whether this problem that you are considering whether it has also been studied under this simple framework of linear regression, and also why whether the noise, if you assume that the noise is a Gaussian and like well behaved, whether you have whether you take advantage of that. So like maybe the general question would be, especially for the students that are taking this class, whether there has been progress on this related to linear regression.
Yeah, that's a good question. So so first of all, I would maybe try and say that the map f of x, right, is nonlinear. So this does not have to be linear at all. So the map relating x to y, so that map f is a nonlinear function of x. So that sort of moves it away from a linear problem. The assumption of additive noise, it is true, and I will make use of it for the first part of the work. For the second part of the work, actually, we will not have to rely on a noise model at all. The machine learning algorithm itself we will assume will create a model for the noise. So this assumption will be made in the first part of the work. We'll be using GANs as priors. But when you get to the part where we're using GANs directly to infer the posterior distribution in Bayesian inference, we will not assume this additive noise model. And coming back to your point about Gaussian noise, most of the times in the linear case, we will, in the first part of the talk, we will assume that P eta is Gaussian.
Thanks a lot. And I guess the last question is whether you assume any relation between nx and ny, whether one is larger than the other.
Oh yeah, no, we don't. We don't. In the examples that I'll be showing, they'll almost be equal to each other, but we've solved other problems where they can be very different, right? So it's like, it is a really good question, actually. So, basically ny represents the points at which you're measuring a response, and nx is the number of points at which you want to infer the field. And obviously the two should be related to each other in some sense. You can't measure response at many places, at very few places, and expect to infer the field on a much finer grid, right? So yeah, but no, we don't really assume any relation in the way we are deriving this. And in most of the examples, they're roughly equal to each other. Okay.
Thank you.
Sure. All right. Let's move on and talk a little bit about Bayesian inference, right? So the starting point for Bayesian inference is Bayes' theorem, which basically just comes out of the definition of what a conditional distribution is, right? So the probability of X conditioned on Y is the joint probability of X and Y divided by the marginal of Y. And then I can take the joint probability and write it as probability of Y conditioned on X times the marginal of X, and that's the formula that we get here, right? But when you apply this formula, which is an identity in a way, to inverse problem, you sort of do it in a stepwise way. So you say there is a state of knowledge that you have up until the measurement, and then you update that state of knowledge after the measurement. And all knowledge about the field that you want to infer, that is up to the measurement, is sitting in this marginal px, which is called the prior distribution. I hope you can see my cursor. I think you can, right? So that is sitting here.
Yes, we do. We do.
Yep. And what you want to get is the posterior. So what you want to get on the left-hand side is now the updated distribution for X given the measurement Y. And what's sitting in here is the likelihood of Y given X, which for, and this is where my assumption of a linear noise comes in, will be simply the distribution of the noise as a function of the discrepancy between the measurement and the prediction of the forward model for a given value of the inferred field, right? And this Z here, which is called the evidence, is basically something that ensures that this numerator here integrates to unity when you integrate it over all of omega X. All right, so that's Bayesian inference as it is applied to solving an inverse problem. And the way to think about it is, I've just rewritten the formula from the previous slide out here, and using a proportionality sign and getting rid of the evidence term here, right? So what you can do is, the first step in applying this is you would construct the prior distribution, which will hopefully be a simple distribution that you can quickly evaluate. And then when you have this, for a given measurement Y, for any X, you can of course evaluate the value of this prior distribution. Then you can evaluate f of X, compute this difference, and knowing p eta, you can evaluate this also. So you know the product, and given that, you can use Markov chain Monte Carlo method to approximate the posterior distribution. There are other methods of making use of this formula, like variational inference, and of course you can do that too, right? Okay, but let's say you wanted to use Markov chain Monte Carlo to approximate this. What are the problems? Like where is the challenge here? So the challenge, of course, is it's pretty obvious, is that when the domain over which you're trying to infer, the dimension of that domain is very large. So when nx is very large, you have to do lots of sampling, right? And NCMC will probably break down after a point, let's say 40, 50, maybe 100. And then the other challenge is characterizing these prior distributions. And I'll tell you what I mean by that for complex cases, right? Now, a typical prior distribution that gets used a lot of time is Gaussian, and that might look something like this. So what you're basically saying here, if you use this as a prior distribution, is that large values of X are extremely unlikely, right? That's what you're trying to say. But compare that with real life, where what you might have is a database of prior solutions or prior realizations of the field that you're trying to infer, which could look like this. So, you know, think of this as maybe the material properties of a very heterogeneous material, where blue is low and yellow is some large value, right? And how do you represent a prior distribution like this? Or maybe let's say it's a natural image. In this case, let's say handwritten digits, and you want to say that whatever your solution is has to look like this. Or it could be some imaging data that you've gathered using some kind of an imaging technique. In this case, it is MRI, and these are slices of a brain which tell you something about the density, right? So how do you encode information like this? And so, you know, a formula as simple as this obviously is not going to work, right? And that's where we are going to start using generative adversarial networks. We will use them for the prior as well as the posterior distribution. But first, let's just talk about the prior distribution. Now, a lot of you who've dabbled in machine learning already know about generative adversarial networks, but I'll again give a very fast introduction. So the way I think about GANs is it's a tool to take lots of samples from a distribution, learn that distribution and then efficiently sample from that distribution. So that's what it does. And what it comprises of are sort of two networks. One is a generator, the other is a critic. The generator will take a latent vector z, which lives in Rnz, and typically nz will be much smaller than nx, right? And it'll comprise of layers of, let's say, convolutions or fully coupled deep neural network layers, and it will produce an x which will live in omega x. So that's what the generator does. The critic will take is a map from omega x to the real line, and so it will either take the true samples of x that are available to you, so x sample from px, or it'll take these fake samples generated by the generator. In either case, it'll map it to a real number r, right? And what it does is, if the sample is real, it would want this number to be large, and if the sample is fake, it would want this number to be small. And the way it achieves that is basically by using an objective function like this. So the expectation of d of x, where x is real, right, and minus the expectation of d of g of z, where z is sampled from pz and then pushed through the generator. So these are the fake samples, right? Now you can imagine that the discriminator will try and maximize this objective function, right? Because it is going to, the critic, it is trying to tell these two distributions apart, whereas the generator will try and minimize this distribution because it is trying to produce samples that are as close as possible to the two distributions, right? So we end up with a min-max problem defined by this objective function under a smoothness constraint. And you can show that when you achieve the optimal for the generator and the discriminator, what you're essentially doing is minimizing the Wasserstein 1 distance or metric between the true distribution px and the push forward of pz by the generator, right? And convergence in that metric implies weak convergence. So what that means is, if you now want to compute some statistic, some complicated nonlinear statistics of x, you could obviously sample from the true distribution of x, but of course that's not really known to you. Or what you could do is you sample z from pz, push it through the generator, and then compute m of that function, or m of whatever you get, right? And then take the expectation over that. And the two are equivalent, right? So this is basically the formula, or this is sort of the property of the GAN that we're going to make use of. Okay, so this sort of weak convergence in terms of densities. And you know, what can GANs do? I'm sure a lot of you have read lots of really cool examples. This example is dated. It's, you know, if I look at the reference here, it's 2017. But this basically, you know, they took images of the faces of celebrities, which are all down here, and trained a GAN to produce fake images of celebrities. So these are the fake celebrities that are produced by the GAN, which are, you know, pretty close if you look at them to realistic looking people. But if you look closely, actually, you start to see some defects. Like, for example, I think like this lady here has an earring on this ear, but does not have an earring on this ear, right? So, of course, there are errors, right? And the other thing I want to make sort of emphasize here is the latent space of this GAN is 512, where so NZ is 512, whereas NX is about 3 million, right? So it has taken maybe a distribution that was defined typically on 3 million dimensions and mapped it down to 500 dimensions, right? So there's a dimension reduction also going on here. Okay, so so that's basically, those are the three ingredients. And now we come to the first part of really what we do, which is how to use GANs as priors. It must be pretty obvious by now, right? Like, what do we do to use GANs as priors? But I'll just walk you through it. Okay, so here is the problem setup. And again, I want to be very clear. The method that I'm proposing will not work in all instances. It will only work if the conditions of this problem setup are met, right? So what I'm assuming is you have a directory of prior solutions available to you, right, of X. So this is an assumption that I'm making right at the beginning, okay? Then you also have available with you a way to implement the direct map, which takes you from X to Y. I'm assuming the noise is additive, and I assume that you know what P eta is. So a lot of assumptions. Mind you, this assumption we've often tried to sort of say, what happens if our assumption is wrong? And the method is pretty robust to that. As people know, Bayesian inference typically ends up being reasonably robust to this assumption. And then, of course, on top of this, you're given a single response y, and you want to infer the distribution of the posterior. So that's the problem that we are solving, okay? And what are the steps with which to solve? So you can imagine the first step is really to train the GAN so that it can basically learn the prior. So we train a GAN using this set of instances of the inferred field that are available, and that's done. Okay. Given that, we can show the following, and basically, in order to show this, what we need to do is simply use this weak convergence formula for the GAN and make use of this definition of what the posterior is in Bayesian inference. And within 2 or 3 steps, you can show that the expectation. Sorry.
Assad, excuse me. Can I just make a quick question? What is the this result is attained for every M in CB? What is CB?
Yeah, so those are continuous and bounded functions.
Ah, okay.
Yeah.
So you can compute the moments.
Yes, exactly right. Basically, it's saying that you can compute the moments. That's right.
Oh, okay. Thank you very much. Sorry.
And in some sense, we actually, we go up to the second moment. So we calculate the mean. We might recalculate maybe the variance or take a square root of it or something, and don't typically go much beyond that. But yeah. Okay. So so just using those 2 formulas, it's actually should be pretty obvious that you can quite easily show this, which is to say that, calculating the expectation of this function of x, where x is sampled from the posterior, is the same thing as calculating the expectation of the same function, right? But with z sampled from a PZ post, so a distribution or a counterpart of the posterior living in the latent space of the GAN, and then you push it forward through the optimized GAN. And the definition of the posterior in the latent space of the GAN is simply this. So it is, the distribution of the GAN that you started with, which is known, which is usually Gaussian, and then, P eta, which is the distribution of the noise model that we assumed. And that's pretty much it, right? So what you can see here is, like, if you give us a y, a measurement, right, for a given z, so we sample from the latent space of the GAN, right, we can certainly find out what pz of z is. Then we push it through the generator, and then we push it through the direct map. We can compute this. If we know p eta, then we can compute all of these terms. So we can use a Markov chain Monte Carlo method on this space, on the latent space of the GAN, instead of the space of x. And that's precisely what we do, right? So you do an MCMC approximation, and you find an approximation of PZ post. And then once that's done, you can sample from that and compute whatever statistic you want to compute, right? So that's
okay. I must interrupt you, but the gain is obvious in point 2. I mean, sampling the latent space is much less costly than sampling the way around.
That's right. No, that's pretty much it. So the ability to represent complex priors. So if you happen to be in this fortunate position where you actually have lots of samples of your possible solution, right, then this allows you to sort of put that in a Bayesian context and make use of it. So that's one advantage. And the other is exactly what Alvaro said, which is that it allows you to sample in a space which is small dimensions. So there's some sort of dimension reduction going on here. And so that's pretty much it. So let me give you a couple of examples of this approach. So we are going to solve the inverse heat conduction problem. Our measurement will be the temperature, which I'll denote, on a finite element grid. So that vector, which will contain the solution at each of those nodes, will be denoted by y, plus, of course, noise. The field that we want to infer is going to be the thermal conductivity kappa, which will again be discretized, and the vector that will contain that will be denoted by x. The forward map is the map that basically takes me from x to y. And it is nonlinear, right? Even though this is a linear PDE, kappa and U appear in a nonlinear way. So it's a nonlinear forward map, right? What else do I want to say? Oh, we implement all of this in Phoenix, and the assumption for the noise is that it's Gaussian IID. So let me move on to some examples here. So the first example we said, okay, let's solve a problem for which we would actually know the true statistics. So we did a very simple distribution of the thermal conductivity. So we said has to be a uniform background, and then an inclusion, a rectangular inclusion within that. And within the inclusion, the conductivity is going to increase from left to right between two fixed values. The only sort of 4 parameters that are allowed to vary are the bottom left and the top right coordinates of the bottom left and the top right corners of this inclusion, right? So we generated lots of samples like this, right? And then trained a GAN with a latent space of 5. So NZ equal to 5, and then asked the GAN to generate lots of samples, and it was generating the samples that you see on the right-hand side. So it learned pretty well the distribution that we started off with. In this case, we took a really simple distribution because, as I'll show you later, we wanted to demonstrate that we could actually compute the true statistics, right? We wanted the right answer. Okay, and so that was the first part of the algorithm.
Sorry. Yeah, I have a question here about the previous one. Maybe I didn't understand, but I guess you would be searching for the corners. Would that be one way to frame the problem?
Yeah, that would be a good way to frame the problem. So if you knew that this problem is, the number of parameters in this problem is 4, right? So it's really 4
exactly. That's what I was wondering. If it's 4, why did you pick 5, right?
Yeah, it's a really good question. So we did try and do 4 also, and it sort of trained. The GAN worked okay, but not as well as it did for 5. So somehow it seems like it needed this little bit of extra room in order to accurately represent the 4-dimensional distribution. Yeah.
Thank you. Okay.
Yeah, that's a really good question. So, but of course, the whole point here is, like in this case, of course, we know that there is a reduced basis which perfectly represents this in 4 dimensions, right? But typically you would not know that. Okay, so all right. So here is how we tested it. So we took a true map of the thermal conductivity that was not used to train the GAN, right? And then we solved the forward problem, which gave us something like this. And then we added a whole bunch of noise to that, which is what you see here. And we said, okay, if this is the measured field, can you predict the thermal conductivity, the statistics of the thermal conductivity using our approach, right? Using the GAN as a prior. And what we found was, this is what we got for the map, or the most likely solution, discretely sampled, right? And if you compare it with the true, of course there are errors, but it's reasonably close. We could compute statistics, so we computed the mean distribution. This is what the mean looked like. But now, like I said earlier, this is a 4-dimensional problem, so we can do Monte Carlo sampling and actually compute the true mean. And this is what sort of the true mean looks like. And they're reasonably close to each other. And then we also could compute some second order moments. So we computed the standard deviation. And you can see that the standard deviation is large around the edges, which is exactly what you would expect, right? It should be able to get the background right and the interior of the inclusion right, but it's not so sure about where the boundaries are. And we can compare them with the true one. And again, there are differences here. And I think these are probably coming from the GAN not being able to approximate this as well as it should. But it's still, I would say, satisfactorily close, right? And then in the bottom, we have a similar example. So this was our validation example. Then we moved on to maybe more complicated examples. So things for which we don't know the true solution. And so we took the MNIST digits, and we and then again trained a GAN to reproduce that. And so the thermal conductivity now looks like 102.1029, right? So that's what it looks like. The latent space of the GAN is now substantially bigger. I think we tried to sort of go to 50 and 20 until about 50 it was okay, 20 started to be not so good, right? So that gives me an idea of the dimension of the underlying manifold. It is probably like, it's got to be greater than 10, right? Because there are 10 digits, but it's probably closer to whatever, 15 or 20. Okay, so so with that GAN trained, we tried to solve inverse problems, right? So here is the true thermal conductivity, right in the middle here. It's a digit 4 that the GAN has not seen before. We solve a forward heat conduction problem with this map for thermal conductivity. We get a temperature which looks like this, add a bunch of noise to it, and then use this measurement and our approach to infer the map, which is quite close to the true solution, the mean, which looks like the map, but the boundaries are blurred if you look closely, and the standard deviation, which is, again, peaked at the edges. So it is not so sure about the edges, pretty sure about everything else. And then we also used this much noise, like this field, and total variation, diminishing regularization to compute the map that way, right? And we basically were not really able to recover this digit 4. So what this is telling me is that we have a really strong prior here, right? The prior is carrying a lot of information within it. The fact that the conductivity has to look like a digit, right? That's a lot of information. And that's why this approach works, whereas something like TV, which would be considered a weaker prior here, will not work, right? But having said that, this approach can get misled, right? So if I now, instead of showing it a handwritten digit, if I started with, I don't know, with something else, like maybe the letter A, it will probably give me something which will look like 8, but not A, right? So it works both ways. Okay, and then we did another example where we started with the digit 7, but removed a part of the measurement, right? So we said, what if this is not available to you? Masked it, and we were still able to get a pretty good approximation to the map, and then can compute the mean and the standard deviation as well. Then going on to more,
regarding your example about A and 8, so basically the trade-off here would be with respect to let's say accuracy versus capacity to generalize across your beyond your original domain.
Yeah, that's a really good point. That is a really good point. I think that is true, Daniel. I mean, I think I would say it in those terms. So mind you, when we get to the second part of the talk, I will talk explicitly about generalization and what works and what does not work in this case. And we're only starting to think about that, but I think there is a trade-off there. You're absolutely right.
Thank you.
Okay. All right. So now we started with a slightly more complicated problem. So the microstructure, so the thermal conductivity has a microstructure which looks like this. To obtain this, we solve the Allen-Kahn equation with different initial conditions and let the simulation go up to a certain point, right? And then using these, we train a GAN. Once again, the latent space is 100, and the number of nodes to represent X is 4,000. So it's a factor of 40 reduction. And then these are the images produced by the GAN, right, which look good. And then once again, we start with the true thermal conductivity, which looks like this. Solve a forward problem, add a bunch of noise, and then show that to our algorithm and use the GAN as a prior to compute the map, the mean, and the standard deviation. So let me say a few things here. Once again, you can see, the boundaries are where the uncertainty is. Okay, so that is true. That's where the standard deviation is also the highest. But if you also look at this carefully and compare the map and the true conductivity, you will see there are significant errors where I've shown these rectangular boxes. So here, you see there is
We lost the sound.
No sound.
Yeah, I believe yes. Your comments, we lost the sound, and I mean, we're not hearing you anymore. Can you hear me, Assad? All right. Well, say something.
It seems your mic is okay, but somehow your connection is messy.
Yeah, unstable, maybe.
It's messy about the soundtrack. Maybe if you leave and get back one.
Yeah, that's probably a good idea, a good suggestion.
As well, turn off and turn on again.
Don't worry, we will be here, don't worry.
Hello?
Yeah.
You can hear me?
You're coming. You're coming, yes.
Okay, so I'm doing audio through my phone now.
All right.
All right. As you wish.
Okay, can you still hear me?
Of course.
Yeah.
Great.
Please go ahead. I think well, the last thing we heard was when they add noise to the images, and you need to say about the difference between the true and the map solutions.
Yeah. So here, I guess what I was trying to point out is in the corners where I have the rectangular box, the true and the map are actually quite different from each other. And there is a good reason for that, because we are imposing Dirichlet boundary conditions on these edges, okay? And so the temperature there is not really determined by the conductivity, it's determined by those boundary conditions, right? So the signal is very low, right? But the cool thing about doing Bayesian inference is, if you look at the standard deviation, that's exactly where the standard deviation is very high. So it's telling you that the uncertainty is very high, and so you should be careful in interpreting the map, right? Which I thought was very, really interesting and kind of a strong motivation for actually doing Bayesian inference for these types of problems. Okay, I'm going to move on. This is some work we did for inferring, CT images based on, the inverse radon transform. But I'll not talk about this. And then I also mentioned that you can use ideas of UQ to actually solve problems in machine learning, and that involves detecting out of distribution samples and active learning. And I'm going to skip on that too. We can talk about it later. I want to come to the second part of the talk, which is how can we use GAN as a way to do to sample the posterior distribution directly. Okay.
Sorry to interrupt. I have a question. Mathieu from Cognitive, a company providing some solution of machine learning. So you are using GAN on priors to try to reduce the dimension of the input parameter of your function f. How does it compare with other techniques of reduction of dimension like variational autoencoders, UMAP, and so on? And is it computationally expensive to generate to sample this prior, to generate new X from your Z for your latent space? Because we know that for UMAP, which work quite well, the computational cost to generate a new X is high. And how does it compare to this kind of techniques?
Yeah, that's a really good question. So I would say that we have not compared this with using variational autoencoders. I would sort of, I have read about people's discussions about the pros and cons of GANs versus variational autoencoders, right? So the variational autoencoders, in some sense, are easier to train, but on the other hand, especially sort of if you look at visual metrics, or you look at metrics which sample, let's say, solution at multiple scale or the texture of solutions, they tend to do not so well as GANs. GANs, on the other hand, are harder to train, and they are hard to train. I mean, we found some techniques which help us in training. So we keep a very close watch on the Wasserstein loss and make sure that we bring it down substantially before we say a GAN is converged. Then we also use some kind of I forget the word for it, spectral something or the other, to help regularize the GAN more. So I think there are trade-offs, but I would say that we haven't really had the chance to explore them very deeply yet.
Okay, thank you. When you say that GAN are more difficult to train, what do you mean by that? Is it you need much more sample, or is it computationally expensive, or in which sense do you use the more difficult?
Yeah, so I use it in the sense of that you're solving a min-max problem, right? And min-max problems by themselves are really hard problems to solve, as opposed to just solving a minimization problem. And so the technique that is typically used for solving this min-max problem is like, you sort of take the gradient with respect to the variable that you're trying to minimize with, take the negative of that, make a step in that direction, then take the gradient of the variable you're trying to maximize with, and take a step in the positive direction for that, and then alternate, right? Now, this technique, even though it's used for non-convex problems, and that's pretty much what we have, there are no guarantees of convergence at all, at least none that I'm aware of. There are people who are working on this. So that, that sort of min-max problem is a tough problem to solve, is what I'm saying. So you run into difficulties of maybe getting stuck sometimes. You also run into the difficulty that it might take many, many iterations to converge. And so those are the things that I'm talking about.
Okay, so the difficulty is related to the optimization part of the... okay, thank you.
Yeah. Okay, so let me come to the second part of the talk. Here, we are going to use a GAN directly to model the posterior. And this builds on some work that is done by Jonas Adler and also by Jonas Adler in the context of, actually the Bayesian inference, and then also Al-Mahiri, who introduced this thing called the augmented cycle GAN. So these are sort of two different worlds, right? One is sort of more the physics world, the other is the more, let's say, machine learning world. And the idea here is the following, right? So now we still have a generator, and the generator still takes a latent space and maps it into X, but it is conditioned on Y. So it's conditioned on the response. So the generator, the input to the generator is one of Z and then one of Y, and it maps it to X. Z is still chosen from a distribution that is well known. NZ is much less than in X, right? But the XY pairs together are chosen from the joint distribution. The critic also takes the XY pair now and maps it to a real number. And what it tries to do is for the X and Y that are from the real world, right? The true X and Y, it tries to increase the value of that real number. And for the pair where the Y comes from the true world, but the X is generated by the generator, it tries to reduce that value, right? So that's what the critic is trying to do. So if you build an objective function which does exactly that, this is exactly what it will look like, right? So this is the part that comes from the true joint distribution. This is the one where Y comes from the Y part of the joint distribution, right? But the X comes from PZ, and as it is pushed forward by the generator. And then what you're trying to do again is solve a min-max problem for where the critic is trying to maximize this distance and the generator is trying to minimize it. And then you can show, if you're able to achieve this optimal solution, then the generator will be such that the distribution of X given Y, right, the conditional distribution, it will minimize the distance between, it will be the thing that will minimize the distance between the distribution of X given Y and the push forward of PZ through the generator for a given Y. So it literally learns that conditional distribution that you're after, right? And again, if it minimizes this Wasserstein 1 distance, then you can say that if you wanted to now compute M of X, where X was sampled from Px given Y, you can do that by sampling Z from PZ and pushing it through this optimal generator and then computing that function, right? So this is the tool that's used to learn the posterior distribution. So let me now set up the inverse problem that we're going to solve using this approach, right? So now here is what, again, this cannot solve all inverse problems. These are the conditions that are necessary to solve the inverse problem. What we need is a sample of X from the prior distribution for X, and then you need a sample of Y, which is sampled from the conditional distribution of Y given X, right? So you need these pairwise data. So you need a set which contains this pairwise data. And then you need a noisy measurement for which you're trying to now find the posterior distribution, right? So that's the inverse problem that we're able to solve. And so the first step is now to train a conditional GAN, and it will produce the generator G of Z, Y, right? And then, just using the formula for Bayesian inference, you can say that the expectation of M of X, where X is sampled from the posterior, is the same as expectation of M of G star of Z, Y, where Z is sampled from PZ, right? So in this case, the sampling involves only using the GAN, right? So if I were to contrast this approach with the approach of using GAN as a prior, right? In one way, it is tougher because here we need pairwise samples. We need X and we need the corresponding Y, right? But in one way, it's simpler because once you train the GAN, that's it, you're done. You just simply sample from the GAN for a given measurement Y, and there is no MC part involved here. So in that sense, it's easier, right? Okay, and that's exactly what I'm trying to say here. You basically, simply sample.
Not easy, but easier, but faster, right?
Yeah, absolutely, it's faster. The other advantage is actually, because if you use the other approach, GANs as prior, right, you need the forward map. And usually if you're doing MC, you would probably use Hamiltonian Monte Carlo because MC, at least for us, by itself does not work. And so what that means is you also need to compute the derivative of the forward map. Here, you can be completely agnostic of the forward map. All you need is the forward map to generate the pairwise data, and then you're done, right? So I think that's the other advantage. Okay, so I've pretty much said this, right? So again, you can still represent complex priors. That's not a problem. You still are working in a reduced space, so that's great. And then I want to say, compared to MC, sampling from this GAN is much simpler because that's all you really have to do. Now, there are a couple of things I want to say here, and that is what basically distinguishes our work from, let's say, the work of Adler or Al-Mahiri, and that is that we use a unit structure for the map that takes us from Y to X, right? And so that's basically for multi-grid people. That's basically like a V cycle, right? So you start at a given, resolution, and there is a transform that takes you from that resolution to X exactly at that resolution. So there is a nonlinear connection there, but then you downsample, right? And then you have another connection there. Then you downsample some more, and then have another connection. That's a typical unit structure. So we use that, and then we use this conditional normalization based on the latent vector. And what that basically means is we try and introduce uncertainty at every level, at every spatial scale. So the Z influences every spatial scale. So those are sort of the two, I would say, unique things about what we are doing, about the architecture of the generator we use. Okay, so now let me end with just a couple of examples of this using GANs as posterior. This is something new that we are doing right now. So, we don't have as many examples, but here we again solving the inverse heat conduction equation. We want to infer the conductivity on a grid of nodes. We are given the temperature on a grid of nodes. And okay, here I want to say that there is no model for the noise that we have to assume, right? The generator learns the model for the noise as well as it can, right? But we don't have to make any assumptions about what the noise is here. Yeah. Okay. So what do I want to say here? So the number of grid points for the response and the inferred variable are the same. So 64 squared. The latent space is 50 here. So there is a significant dimension reduction going on here as well. And now keep in mind, in order to train the GAN, we need pairwise samples. So this is, the thermal conductivity. We solve the forward problem and add some noise here, right? So we are sort of adding our own fake noise. And this is the measurement. And this is yet another sample. And this is a measurement, yet another sample. And this is a measurement. And so there are, how many? So we use about 8,000 samples to train the GAN. And once the GAN is trained, it will produce images like this. So it will produce the, sorry, I want to take it back. These are all samples that are used to train the GAN. All right. So the result from the GAN is in the next page. Okay. So now we solve the inverse problem or the inference problem, right? So this is the target thermal conductivity. All right. So we solve the forward problem, add noise to it. So this is the measurement, right? Now so remember, this is a conditional GAN. So this measurement will be an input to the GAN, right? And then there will be the latent space. And we can sample over the latent space. So we sample over the latent space to generate the mean, the map, and the standard deviation, right? And so you can see that the mean and the map look a lot like the target. And the difference between, let's say, the map and the target is very small. And once again, the uncertainty is largest at the edges. That's where it's most uncertain about, what the thermal conductivity is. But it's also interesting that the uncertainty is larger over where the thermal conductivity is larger. And that also makes sense because you can think of like the thermal conductivity going to infinity. The temperature will reach a finite limit, right? And so a small perturbation in thermal conductivity, when it is very large, will cause a very small perturbation in temperature. So again, the sort of the noise to signal ratio, let's say, is going to go down as the thermal conductivity increases, and therefore your variance should actually go up in those regions. And that's what you see here. All right. So this is for one measurement. Here is for another measurement and yet another measurement. And you can see, it works well. So now this is where we also tried to test generalizability. So this GAN was trained on exactly these distributions, basically circular inclusions anywhere in the domain. So we said, what if we showed it, the target in this case is 2 circular inclusion, and the temperature field corresponds to the temperature field with 2 circular inclusions. It has never seen 2 circular inclusions, right? Then the question is, what kind of answers do we get? So we get here, this is the mean, this is the map, right? And we actually do pick up 2 circular inclusions. It's not as good as it was earlier, because if you look at the difference between the map and the true distribution, it's bigger, right? And the standard deviation is also, whatever. It sort of follows the trend from before. So this was interesting. So then we said, okay, what if we bring these inclusions closer together? So we took 2 inclusions that were closer together and took that temperature field and then gave it to the GAN. And it was somehow able to produce the second inclusion, but it is much weaker than it really should be. And then at some point, if you bring them, if they're strong enough and you bring them together, even though the target has 2 circular inclusions, the reconstruction has only 1, right? So this was interesting in the sense, like, what's going on here, and so, well, I'll come to that in a second. I'll probably end with that, and so we tried to see how it generalizes in yet another way. So in this case, the target was an ellipse, and this is the temperature measurement corresponding to that, and this is the mean and the map that we got. And basically what it tried to do was make the ellipse more circular, right? And of course, if the target was an ellipse that was probably more circular to begin with, it actually did a pretty good job, which is down here, right? So here's what we've observed that can help to explain this. What we observed is that the unit structure actually induces a map from the response to the solution that is spatially local, okay? So if you look at that, so we computed the derivative of dx dy for a given value of x, and what we found is that it is peaked exactly where that x is, and then it decays after that, right? So it introduces some sort of a locality, which explains when these inclusions are far away, right? It treats them as separate inclusions and has no problem getting the right answer. But when you bring these inclusions together, then it has no other choice but to sort of bring them together into a single inclusion. So the point is, that's where the generalizability is coming from. The generalizability is coming from the architecture of the UNet. If we change the architecture, we'll get a different type of generalizability, which makes complete sense if you think about it, right? It can't be magic that you train it on circles and it works on a single circle and it works on two circles. The only reason it works is because the architecture is telling you that if these things are far enough apart, they don't influence each other. So it has learned that. Okay, well, maybe I will end with this one where we've actually applied the same idea, but to a problem in medical imaging, where often the challenge is, you take an MR scan of the brain, which is what this is. The first thing that the clinician wants to do is get rid of the skull and the meninges, so that they can focus on the brain itself, right? So they want to go from here to here. And this is, you can imagine it's relatively easy to do in an image like this, but once you start including, once you come down to slices here or here, then it becomes more challenging because you've got the eye sockets and then, what is the brain and what is not the brain becomes more challenging. So what we did was we took a pairwise data like this from many subjects and then trained a conditional GAN of the kind that I just described before. And then, then we gave it an input like this, and this was the output that was produced here. Sorry, this is the output that was produced, and this is the target. This is what a human would actually carve out as the brain, and you can see that there isn't much of a difference. And you can also see that when you come down to the really challenging part, which is where the nose is, in this case, the brain part that the clinician is interested in is in 3 distinct locations, and it's able to gather that, right? The interesting thing is, since it's, again, a stochastic algorithm, we can compute things like, the mean as also the standard deviation. And here, in this particular example, this was the target. The mean produced this incorrect region here. I hope you can see it, but that's exactly where the standard deviation was large, sort of letting you know that it is uncertain about that. So that's the utility of actually doing UQ in a computer vision problem like this. Okay, I think I'm going to end with some conclusions. I do want to contrast these 2 different methods that we talked about today, GANs for priors, GANs for posterior. As I was saying, if you look at the training data, this only needs X from the prior, does not need anything, any images of the response to train it. Whereas in this case, you need both those guys. So you need the pairwise data. Here, you need the forward model, and often you need the gradient of the forward model, df dx, for the MCMC part. Here, it's not needed. Here, you have, there are 2 sort of sampling that needs to be done from the GAN as well as MCMC. Here, it's simply GAN. And here, generalizability is a little hard to control. I don't know exactly how you would control it. Here, you can control it. Here, if you tell me that the map between X to Y is very local, right? I can construct a unit architecture that will preserve that locality. I can embed that generalizability to the algorithm. On the other hand, if you tell me it's very, very global, then I will come up with a different architecture. So there is a way to control that. And I think that's an interesting idea to explore further. So, I'll conclude by just acknowledging some funding agencies for their support, the Army Research Office, Airbus, and an institute at USC. And I'll take questions and obviously maybe just point to these references. This is a nice article on inverse problems I would recommend to everyone. This is a good treatise on Bayesian inference. This is the original GAN paper. This is a nice book which talks about optimal transport and convergence in Wasserstein distances and things like that. This is the Wasserstein-Gann paper. This tells you how to, no, this is not that good. I mean, this is the paper by Adler, and this is, the second part of the talk is based on this. This is augmented cycle GAN, also the inspiration for the second part of the, and this is, some work that we have done that puts some of these ideas together. Okay, I will stop and take questions.
Thank you. I mean, thanks, Assad, for a very nice talk. And well, the floor is open for questions. Please shoot. Alex, Fernando.
Hi, Assad. Very good presentation. Thank you so much. I was heading back to the GANs as priors. I was thinking conciliating your ideas with like expert knowledge. So expert can generate just a small bunch of plausible X's for you. Like a doctor can think about a little bit before image. And there is some GANs formulations that would deal with the small data routine. Have you considered this before?
No, I haven't. But that's a really, that's an excellent idea too, I think, right? So an expert, since it's human, hopefully, or not hopefully, will most likely not be able to create tons and tons of samples, right? But like you said, there are formulations of GANs that sort of take a sample and break it down into smaller spatial regions, and then learn the sort of the relation between those spatial regions at multiple scales. And you could certainly train those and then apply these ideas. But also apply the second part. If you then knew what your forward map was, you could take those samples and run a forward map on it and generate lots of Ys also.
Sure. Right. But a part of the uncertainties would come from the small data, and that will when you see the standard deviation, you don't know how to disambiguate what's the uncertainty, general uncertainty, and the lack of data. That's what
that's a good. So I think you're right. So the error between the distribution learned by the GAN, which is nothing but an approximation to the true distribution, that will increase, and that will contaminate the solution for sure. Yep.
But anyways, you have to do that in some sense, because many times you have small data, and you don't want to lose your experts' knowledge accumulated for years.
Yeah, I agree.
Thank you.
All right, we have another. Ismael, please go ahead and introduce yourself, please.
Hi, Assad. Hi, everyone. I'm Ismael from Petrobras Research Center. Thank you very much, Assad, for your great presentation. Maybe I have a silly question, but I understood that using the GANs as a posterior is a very interesting point. But I couldn't barely get the point for doing this, because you have to sample from the conditional distribution from Y to X, for example. And you maybe, if I understood correctly, you would use a UNet for infer this conditional distribution. Can you explain a little bit again? Because it was, there's something that I couldn't.
I agree. Good point, Ismail. I don't think I made the point clearly enough. So let me give you a very specific example, right? So let's say you're from Petrobras, and I'm sure you have legacy codes that can do amazing things, right? That can solve amazing forward problems for Petrobras, right? Now let's say you want to use those legacy codes to solve inverse problems. And what you would like is a method that is non-invasive. You don't want to go in there and take 20,000 lines of Fortran code and then somehow change things. So you certainly don't want to do that, right? What you could do is generate, so whatever the input field is, so let's say permeability, you could generate lots of possible solutions, lots of likely scenarios of what permeability might look like, right? Then you could run each one of those through your super duper forward model, which will produce whatever response that you're interested in, maybe the pressure field, maybe something else, right? And then you will have this pairwise data available to you. You take that and train the conditional GAN. And what the conditional GAN will do is, the next time, even if you give it the pressure field measured at a few locations, it will produce the probability of the permeability field, right? The statistics of the permeability field that will be consistent with that pressure field, right? And this is done without ever having to go to your legacy code and change it. You don't have to make any changes. The only thing you have to do is, make a guess of what are the possible permeability fields. What is the spatial, what do they look like? Generate a library of those and solve a bunch of forward problems, and then train the unit, train the conditional GAN that I talked about. And then you can use that to solve an inverse problem. And not only, a deterministic, but a stochastic inverse problem. So I think that's the utility.
Okay. So it's kind of a conditionally training of the GAN based on the legacy code that I have, so I can use at the end the results from this GAN.
I mean, we've run into these applications, right? We have like fluid code that has all the bells and whistles in it, right? Now, if you want to solve an inverse problem using that, usually you have to go in there. At the very least, you have to compute gradients. You have to sort of, compute df dx, and that's not easy. Right. But on the other hand, it's very easy to run it multiple times. It's embarrassingly parallel. You can do it. All those things are easily doable. And so then you can build a conditional GAN for the inverse map using this idea. So I think that's where it's useful.
Okay.
Yeah.
Okay.
A database of, pairwise solutions for your quantitative interest, and then use this training again and forget all about this. It gives you new data, and again will generate the answer for you. That's the beauty of all this.
Yeah, my confusion was because in the transparency that you showed before, you mentioned that you avoid doing the Monte Carlo. Yeah, that one. Because no need to do. Okay, but okay, you still need to do some Monte Carlo, Markov Monte Carlo.
Yeah, no, only in the sense of like once you decide, you still need to generate samples of the field that you want to infer, right? And what they look like. So certainly you need to do that. But you don't need Markov chain Monte Carlo anymore, right? You take that and you sort of solve the corresponding forward problem and get this pairwise data, and then you train the GAN. You don't need them.
Yeah, it's not a bunch of simulation. It's not needed because I have this legacy code for doing this. Okay, I get it.
Yeah.
Another question that comes with this is how many evaluation of your legacy code you have to do to be meaningful. I mean, to cover as a distribution. That's another story. But even this, right? Could be practical or not. Could be practical or not. But that's a problem-dependent issue.
Yeah.
Right.
I agree.
Yeah. Am I right? Yeah.
Yeah. Can you hear me? Yeah.
Yeah. Of course.
Yeah. No, you're right, Alvaro. I mean, I think it's a really important question. How many simulations do you really need? Again, I think it's like, what is the underlying manifold on which this data exists, right? That would determine that. So like, for example, for the problems we were solving, I think I showed you, we did about 10,000, right? I think roughly 8K samples. And you could argue these are very simple problems, and for more complicated problems, you would need more.
Wow. That's life, and life's complicated. What can we do? We have to pay for the statistics.
That's right.
Well, Any other questions from the floor? Danielle, I mean, you asked so many questions during the talk. Now you're done, right?
Yes. Thank you so much. Yeah, that was,
I'm very glad to see you here. See you around. Thanks for coming.
Thanks for the opportunity. Yes. I would like also to hear more from the students. So we have students here from the course that Claudio Micelli and I are sharing. So guys, if you have any questions, please take the chance, because
enjoy the opportunity. I mean, because we are having the pleasure here to have Assad Oberai with us, with one of the experts on the field, you know.
Exactly.
And don't be afraid, he doesn't bite.
I can't. I'm so far away. There's nothing I can do.
Yeah. Only bark.
Right. That's okay. Anyway. I mean, I do want to extend the invitation for anyone to sort of send me email and ask any questions. That way, we can always set up a Zoom chat, or we can set up a meeting to chat later. No problems.
Yeah, thanks a lot.
Can you send us the presentation later?
No, I mean, everything will be. I mean, the slides will be at ResearchGate in our project where all the talks are.
Oh, okay, perfect.
And I will upload this to YouTube, the talk to YouTube. Okay.
That's great. Thank you a lot.
I will stop. I'll stop recording so we can be more relaxed right now, and maybe the students will. Okay, thanks a lot. I will stop recording right here, and we can continue if Assad will be available. Okay.
Thank you, Assad. It was great. It was great.
Let me let me stop just 1 second.
Thank you, Assad.
Thank you, Assad.
Sure.
Yes.